With this short presentation, I'd like to describe the way collisions are avoided in air today, and then to describe another way that would have a number of advantages. Today's operational collision avoidance system is called TCAS. TCAS resolves conflicts by what I'll call a sudden vertical dodge. One aircraft climbs while the other one dives, like this. Immediately you can see some limitations. For example, it can't be applied to runway incursions, which account for a significant percentage of the accidents and near-miss incidents involving aircraft. Also, the sudden, last-moment character of the maneuver makes a lot of people wish for a more gradual, more gentle course of action. No criticism is intended here towards TCAS. It was devised decades ago. That was before GPS. That opens the door to an explanation for the choice of climbs and dives instead of horizontal maneuvers. Transponders are used for timing of pulses transmitted and responses received. We know the speed of signals transmitted back and forth, depicted by those zigzag lines in this sketch. That's the speed of light. So, that timing enables determination of distances between aircraft. But distance isn't everything that we need. For example, note the aircraft that appears closest to us, the largest one in this sketch. If the other two aircraft are the same distance away from that one, then all the signals to and from it will take the same amount of time. But we also need a timely and accurate determination of the direction, north, south, east, west, and that just isn't available from all those transponder measurements. Now I want to begin an abbreviated description of how a number of problems can be solved. There's more to this than a short presentation can cover, so I'll just make some basic statements. With GPS measurements, full three-dimensional information can be maintained in track files for all aircraft outfitted with the right equipment. Nothing new has to be invented. The equipment includes Mode S, already widely used, plus GPS receivers with the measurements available to be transmitted over data links. With spontaneous transmission, during assigned time slots, of GPS measurements, we get cancellation of the major error sources, and every participant can track every other participant. What follows now is a simple example that treats the flight path of a tracked aircraft as if it were known. Obviously, that's an idealization, but with GPS data available, it isn't far off the truth. Errors in tracking from GPS are much smaller than the missed distances separating the aircraft. The intended emphasis here is on guidance. With that in mind, we're ready for a little illustration. This is the blog that explains more about this subject. Here's a scenario described in the blog entitled Collision Avoidance by Deceleration, involving two aircraft initially on a collision course at co-altitude. I set up the coordinates so that without any evasive action, a collision would happen right here, 0 meters north and 0 meters east, and I made that the origin. The aircraft near the lower right corner, designated by the blue O right there, he's the evader. He evades a collision by decelerating from 450 knots to something less than that northbound. He will fly this way, in this direction. And the amount of speed change will be enough to produce 1 kilometer miss distance at the point of closest approach. The intruder, designated by the black X up here, starts out near the upper left corner at about 20 kilometers west of the origin, 20 kilometers west. He will fly in an east-northeast direction, about like this, at a somewhat lower speed, 350 knots. In a few moments, the motion will begin. First, I want to explain that the range of coordinate values will suddenly be increased. Then the intruder's symbol, X, and the evader's symbol, O, won't be obstructed by these coordinate grid lines the way it is right now. Okay. You see both of them moving, and the evader doesn't reach the point of closest approach until after the intruder flew past it. Still, it looks close, and that might look scary. So this is where I have to remind anyone watching this of several things. The first point is that the scale of the plot covers about 20 kilometers in the east-west direction and more than that north-south. The ordinate and abscissa have different scales, partly because of the different speeds. Point 2. The closest approach separation can be controlled by program input. The only caveat is that extremely large separations can require impractical amounts of speed change. The third point. In order to prevent a wake problem, the evader includes a gradual climb, aiming at a point above the origin. That results in a vertical separation half as much as what TCAS provides. Here the other aircraft doesn't dive. The fourth point. Here there's much more separation horizontally than there is vertically. And remember, TCAS isn't designed to provide any horizontal separation at all. Point 5. In marked contrast to TCAS, this evader's velocity adjustment can be gentle because they are made much farther in advance. And finally, point 6. By maintaining a continuous track of the intruder, this evader's velocity adjustments can be repetitive, which enables each new adjustment to correct for any previous control imperfections and for any new information that could come from unanticipated changes in the intruder's flight path. Now I'd like to show that it's also okay for the evader to use a speed increase. Here's another scenario with the intruder flying east-southeast. All right, here we will put in the same scenario almost. Again, we will give it 120 seconds, 2 minutes before the time that a collision would have occurred. The miss distance will again say we want 1 kilometer. And again, we'll use the same speeds, 350 for the intruder and 450 knots for the evader. But this time, the direction will be east-southeast, so that would be this heading. Now we go to the figure, and once again they're starting out with the evader near the lower right corner and of course the intruder in the opposite corner. Okay, here we go. Now this time you'll see the evader gets there faster. He increased his speed instead of decreasing it. It really doesn't matter how he does it as long as he gets there at a different time. I'll conclude this by admitting that there's no official authority backing this. I don't have authority to commit resources for flight tests, but I'm working with some people who do have that authority. There aren't any imminent plans, any big plans to put these ideas into practice anytime soon. There are hurdles to overcome before that can happen, and that's understandable. Flight safety demands a gradual approach to changes. But hurdles are not the same thing as a brick wall plus a moat full of crocodiles. I mean, yes, there are hurdles, but what we are able to say is that if and when these possibilities are taken advantage of, that there is a lot of real potential here for avoiding collisions both in the runway incursion situation and in air.